Hi, I'm John Duggan, and this is the TheoryStation. This program is the Principles of Math program. The series is Basic Ideas. This is the 9th installment in the series. So up to now we've covered a number of different ideas. In the previous installment we were talking about calculus and how that could help us in thinking about optimization problems. That is, we were trying to find where a function took its highest value, where the function was only defined on single numbers. So now I want to extend those ideas to think about multivariate functions and maximizing those things. So to start, I'm actually going to go back to the topic of equations. We talked about equations before, and there we were thinking about linear equations. Now I want to just push a little bit in the direction of nonlinear equations. And just to recap a little bit from the linear case, there it was pretty straightforward, and when there weren't very many equations and variables, then, easy to work with. So an example would be, let's say 3/2 x plus y equals 6 and minus 1/2 x plus y equals 2. So there's a system of two equations and two unknowns. Algebraically, we could just solve that straight away. But geometrically, it's worth thinking about as well. In this case, the set of xy pairs that solve the first equation form a line in the Cartesian plane. So that's going to look something like this. The vertical intercept is 6, and the slope is minus 3/2. And I can get that by just transforming this equation and writing it like so. Okay. The second equation, what do the xy pairs that solve the second equation look like? Well, let me transform it similarly, and we'll do y equals 1/2 x plus 2. So the set of xy pairs that solve the second equation will look something like this, where the intercept is 2 and the slope is equal to 1/2. And as long as those lines are not parallel, they'll intersect somewhere, and they'll have, as long as they're not the same lines, they'll have a unique intersection, and that gives us our solution. Okay. We can do the algebra really quickly. So we know that at that solution, we know that y is equal to minus 3/2 x plus 6. It's also equal to 1/2 x plus 2. So that means that those expressions at the solution have to equal each other. And so if I subtract 2 from both sides, and I add 3/2 x to both sides and simplify, I get that 2x equals 4, so x is equal to 2. So I can substitute that back in, and y is equal to 1 plus 2, which is 3. Okay, so again, conceptually, linear equations are pretty straightforward, but suppose we have a nonlinear equation. So let's stick with the first equation, which is linear. But now let's throw in something that's a little bit different. I guess I'll use, well, 6 again. I don't know why I'm using 6s for right-hand values, but anyway. So now the first equation is linear, but the second equation, we're not adding x plus y. We're multiplying them together. That's a nonlinear expression. And if we were to graph the solutions to those, well, again, the xy pairs that solve the first equation, they're the straight line, vertical intercept of 6, slope minus 3/2. What are the xy pairs that solve the second equation? Well, we looked at something like this when we were doing talking about functions. Again, we can just here I'm just going to well, obviously to solve that x has to be non-zero, so that means that we can divide by x, and so the set of xy pairs that satisfy the second equation will satisfy this relationship, y is equal to 6 over x, and we can plot those points. That's going to look something like, well, there's different possibilities. One possibility is that it's a curve and it never intersects that line and there's no solution to this system. Another possibility is that the curve intersects the line like so and there's two solutions. And then a last possibility is that it touched the line but only at one point, so that there's a unique solution. Okay, so let's just go ahead and try to solve these equations and see what we come up with. So if we just make the substitution and put that in the first equation, we get this. We know at any solution, if there is one, y is equal to 6 over x. We also know 3/2 x plus that is equal to 6. So if we solve this thing, we get 3/2. If we multiply both sides by x, we get the following equation. Let's subtract 6x from each side. So for x to be part of a solution to these two equations, it must solve this quadratic equation. Remember the quadratic formula. For a general quadratic equation in x with coefficients a, b, and c, the solution, if any, or solutions plural, is minus b plus or minus the square root of b squared minus 4ac all over 2a. So in our example here, x would be equal to negative b is 6 plus or minus the square root of b squared, which is 36, minus, well, it's going to be minus 4 times a times c all over 2a. So let's simplify that. That's 6 plus or minus what? So in this square root, we have 36 minus, well, 4 times 3/2 is 6, times 6 is 36, and so that actually is going to go away, and 2 times 3/2 is 3. Right, the square root of 0 is just 0, and so we end up getting 6 over 3, which is 2. So it turns out that for x to be part of a solution to these two equations, it has to be equal to 2. So that tells us that we are in this the case of the blue curve here, where there's a unique solution. And of course, if x is equal to 2, well, 6 divided by 2 is 3, so that gives us our value of y. So there's a unique solution to this system of nonlinear equations, and again, that does not always have to be the case. There can be no solutions, multiple solutions, but I picked this example to be super simple. So with that, I think we've done enough on nonlinear equations, and the next step would be to apply that stuff to help think about constrained optimization theory. I think this installment's going a little bit long, so I'll end this here, and I'll start up again in installment number 10.